Okay, thank you for the introduction. So this is joint work with Nachi, that is sitting somewhere in the audience. And yeah, let's get to it. So first I will start with a small introduction of what is information flow control and what it tries to achieve. So basically the idea is that we have programs, and these programs manage some kind of data. So what we want is that these programs preserve the confidentiality and integrity of this data. And to do so, we analyze flows in a program, how the data is handled by this program. And basically what we want is to reject the programs that might leak secret data into public sinks. Okay, so more specifically, normally the property we want to show is this thing called non-interference. So here we have the program as some kind of black box that gets some secret inputs and some public inputs, and produces secret outputs and public outputs. And basically the idea is that if we have an attacker, so the flows we want to allow are those that go from public to public, from public to secret, from secret to secret. But if we had a flow that went from secret to public, then we should be able to reject this program, because this is a flow that might reveal some secret information where it shouldn't. So more specifically, we can characterize this property with this formula that basically states that if we run program P with any two different secret inputs, then the attacker shouldn't be able to observe this. This is the small L in the quality after running the program. So basically for him it's transparent whether we pass X or Y as an input to this program. Okay, so how do we prove non-interference? And this is the key idea of our paper, that we can show that non-interference is a syntactic property of normal forms, that for now it is enough to think of them as some kind of simplified programs. Okay, so this is nice because it's very syntax directed. We can just show this by induction on the normal forms, and it's simple, and this is something I will argue for later. Okay, so the basic idea is now what everyone does is, suppose we design a new language and we think it's secure. Of course, everyone thinks their languages are secure, but how do we show it satisfies non-interference? And in this work, we only consider the confidentiality part of security, not the integrity part. So, and for this, in the literature, there are a bunch of approaches. So basically, we have like this seminal work by Abadi et al., where they prove this using the notational semantics for the dependency called calculus. Then we have a lot of work on term erasure by a lot of people and some people in this audience. And also we have some work using parametricity that is more related to the notational semantics. So what do we add here? Basically, we can see our idea as, let's take this program and let's inspect it. Okay, so we inspect the syntax of the program. Now the problem is that if we just take the program and try to analyze what is done by looking at the source code, this is very complicated, because like programs are like complicated structures. So the idea is simplify these programs and then do this inspection, and then see from the simplification that the programs are non-interferent. So the contributions of our work, we present this proof method for non-interference based on normalization of programs, and we have verified our results in the Agda Proof Assistant. Yeah, so in the rest of this talk, I'm gonna go more in detail on an example and then kind of give the intuition of how this generalizes to more programs, and then we will jump to some conclusions. So to do this, the basic calculus that we take to study our approach is this thing that we call Lambdasec, that is based on a static IFC calculus that was from some paper from Alejandro Russo et al. From 2009 that is implemented as a Haskell library called seclib. And basically the idea is that in this calculus we have this data type, this monad S, one monad for each point in the lattice. The lattice is static information. And then we have some primitives, that is basically what you would expect. You have return to put something inside the monad. So this label L can be either high or low, depending on whether it's secret or public. Then you can sequence computations using the bind. And basically, the interesting part is this app combinator that, supposing that we have a computation of some level L low, in this case, we can upgrade the secrecy of this computation to something high, if this respects the security lattice. This is the idea. And intuitively, we can see that this is a secure calculus, as monads are sticky, you cannot escape them, and the only way to actually transform something of a monadic type is by the app combinator that only lets us go up in the lattice. So this intuitively should be secure. Okay, now we go with the example. So let's suppose we have this program F that takes a secret boolean and produces a public boolean. This is something in the monad with label H and produces something with label low. Okay, so for example, what kind of programs can have this type? This is one example of this of a program that satisfies this type, that basically does nothing with the secret, but does a bunch of stuff and then returns a value. Or this other program that is even more complicated. And the idea here is that just by the type signature of this program, we cannot tell anything, whether it's leaking the secret or not. For example, this other program that just binds some computation and flips the boolean, but does nothing with the secret. And the intuition here is that all these programs have something in common, that is, they don't use S to compute the end result. So intuitively, the message is that any secure implementation of F is constant, in the sense that the secret is not used to produce the final value. Okay, so how do we use our idea to show this? So basically, we have all these programs that are very complicated, and we normalize them to these normal forms that I will explain shortly. And the idea is that then we can inspect these normal forms and see whether they are constant or not. And we can think of these normal forms as some kind of values, so we can quote them back into programs. So they are really some kind of program in some way. So what are these normal forms that I've been talking about? So I will explain them by explaining what is not a normal form. So in this case, we have this computation, and because everything is well defined here, we can just beta reduce. So return true bind, it will push the true to the continuation, and then we do some beta reduction, and now we apply the function node, and now finally we get an actual value. But the idea of normal forms is, what if the left-hand side of this bind operator is an unknown variable? It's something that we don't know yet. So this is the idea. If we have this term, we cannot compute anything about it. We cannot look and say, oh, say anything useful about this. But this is the idea. Normal forms are open terms type in context, that do not reduce, that are blocked somehow. And the idea is that we can characterize them as this pair of syntactic categories, that is normal forms and neutrals. And the idea is that neutrals represents those terms, those variables that depend on something of the context, but that is undefined at this point. And we will see shortly an example. So why do normal forms help? So intuitively, like in the return case, a normal form is just some kind of value that we say, okay, return t is a normal form when t is a normal form. But now we go to the interesting case. That is, if we have something, if we have a monadic bind, and the left-hand side of the monadic bind is a variable, is a neutral here, then this thing is a normal form, because we can see that we can not do anything with this. This is blocked for reduction. And the nice thing about these normal forms is that, and this you should trust me, any normal form of this monadic type is going to be one of these two. There is nothing else. There is not going to be function application or anything else. And this gives us the syntax-directed proof that we are looking for. So how we use this? So we go back to the example, and we can prove a lemma like the following that says, in any empty context, a normal form of the type of the function that we were looking at before, so this one that takes a secret input and produces a public boolean, is either going to be lambda x return true or lambda x returns false, and nothing else. Like, it's going to really be one of these two functions. And how do we prove this? Of course, we look at the normal forms of this type. So here I'm going to go through the proof sketch. So we start with this, and we say, oh, we have we want a normal form of this type. And this I haven't explained, but the only normal forms of the function types are lambda x dot something. So we reduce this to showing, okay, I have lambda x dot something, and now I need something to fill this hole. But for this, we push the argument into the context, and now we look for a normal form of type public bool. So here, as I said before, the only two ways is either we have a bind or we have a return, and there is nothing else. There is no other normal form of this type. So if we go to the bind, okay, we are looking for a neutral, if you remember, the yellow box, and the gray box is a normal form. And here is the catch. To find a neutral of this type, it has to be something that occurs already in the context. And this was the intuition I gave about neutrals. Neutrals are always something that occurs in the context. So this path, we don't have it anymore. Now we go the other way and we have, return of something. So we do again, if we have return, then we need something of type bool for this to be a normal form. And the only two normal forms of type bool are either true or false. So basically we have constructed that every normal form of this type is gonna be going up lambda x return false or lambda x return true and nothing else. So this is really the lemma we were proving just by looking at the syntax of normal forms. And now how does this help? Because this is very contrived to the normal forms of this type, but what we want is really a general theorem about any function of such type. So this is where normalization kicks in. So basically normalization is just finding these normal forms, and to do so we implement it using this technique called normalization by evaluation. That basically we use some meta language to evaluate programs in the object language, and we have this function norm that basically if you give me a program that is written as a derivation from a context gamma of type A, then I will give you a normal form. And what we expect from this function norm is that at least it's correct in the sense that a program and its normal form are equal respect to beta eta. So they are equivalent programs. And this is really what gives us the following theorem that we call noninterference for this program f, that basically says any function of this type that we were looking at before, we have that for any two secrets, f applied to the first secret is going to be equivalent to f applied to the second secret. And the proof really follows from the fact that we show that f is constant, the normal form of f is constant, and the program, the function f is equivalent to its normal form. And then we can show by beta reduction that this holds. And this is basically the intuition the proof we have. Okay? So now I'm gonna explain a bit how one could generalize this further, because this is just for this program f. So, yeah, we have shown that f is non-interferent, but does this scale? And unless the answer is yes, I wouldn't be asking this question. So yes. And how do we do so? So the idea now is in this, for the program f, we characterize what means for it to be constant. So maybe we can characterize in a more general setting what are constant terms. So for this, we have this definition that says that a program f is constant if for any two substitutions, applying the substitutions yield equivalent programs. Okay, so now how we show that a program is constant? So basically we have this lemma that says if you give any program of type A where gamma is protected at level h, this means that everything in the context gamma is going to be a secret, and then A is visible to the attacker that is at level L, then all these programs are going to be constant. So we have that for any two substitutions, they are going to be equivalent. And the idea is, how do we prove this? Again, basically what we do is we inspect the normal forms of this that corresponds to this type, and then we have our proof. I'm not gonna go into it, but I recommend you look at the Agda formalization or the paper. And basically this gives us this more general theorem that we call non-interference for Lambdasec, that says that given a program f of this type, for any two low equivalent substitutions, they are going to be equivalent programs. And the intuition here is that low equivalent substitutions are those that agree on the public parts but differ on the secret parts. And the idea is if we apply first the one that agrees on the public parts, then we deal with two terms that are type in protected context. And now we have shown that any term that is typing a protected context is constant. So I can apply the high substitutions, and then I'm gonna have the same program. And that's basically the idea behind this proof. Yeah, so I'm gonna jump into the conclusions. And again, this is the idea that we want to transmit, that non-interference can be shown as a syntactic property of the normal forms. And this is the take-home message. So what we presented is a proof of non-interference by normalization. And the idea is that our setup is very narrow to this language that is not very expressive in some sense. But what we conjecture is that we could use similar techniques as type-directed partial evaluation to show this for more expressive languages. In the sense that you don't analyze the program, but you analyze some simplified version of the program, and you can show by a syntactic proof that they satisfy non-interference. And for the technical details, please read the paper or check the ACDA formalization in this webpage. Thank you for your attention.
Thank you. Again, plenty of time for question.
Hi, thank you for your talk. This is very interesting. You said you were looking at scaling this to more expressive languages, and I was wondering what sort of thing you had in mind. What other expressive forms would you like to have?
So basically, this heavily relies on the language to be a strong normalizing. So the first step will be, can we add a fixed point? Can we have non-terminated programs and still do this kind of proof for languages that have like general recursion, for example? This is the idea. Can we do something similar, like by partially evaluating these programs, can we show some kind of non-interference just by looking at the syntax of the simplified version of the programs? This is a bit the idea.
Thank you.
Okay, my question is about this statement that non-interference is a syntactic property, and I always see this example, this x minus x example, where you have a program where you get a high input and all you do is output x minus x. And I'd imagine this one, so this one is not syntactic, right? You need to, unless you had some sort of equational reasoning to show that x minus x is 0, you won't be able to show that's non-interfering. So how is that handled in your scheme?
So what we characterize is really the kind of programs that depend on secret inputs should be constant in the sense that they do not use to compute. If you are doing x minus x, this is a forbidden program. In the sense that for doing x minus x, you should expect what x is. So the result, even though it's going to be the same for every input, depends on what you have as an input. Like this is less expressive that it cannot handle your example.
Okay, so you're not saying that you're doing all of or what everyone thinks is non-interference, or the most general definition of non-interference is not necessarily handled by your kind of analysis, right? It's restricted to a subcase. Is that what you just said?
Yes.
Right, so if you define non-interference as the output should always be the same regardless of what happens inside, then x minus x does not interfere in that program.
Yeah. Okay. Yeah, so you're right.
Yeah, thank you.
Oh yeah.
Hi, thank you for the talk. So question is about extending this framework. And so to explain my background here, I'm not a very PL person. I actually do hardware and side channels. I'm getting laughs from the cloud. But so the question is, how easy would it be to extend this into timing, given you don't extend the framework? If you don't extend the language, but you extend it into timing in non-interference.
Timing. That's a good question, actually. So, so for the timing part, you will need some kind of semantics that keeps track of timing,
Yes.
right? And I don't know, maybe it can be done, but I really don't have an intuition how.
I see. Okay.
How we will extend this to like this kind of PSNI,
I see.
Progress sensitive.
progress sensitive non-interference.
I see. Okay. Perhaps if we have a way of typing or doing inference on if and conditional expressions, that would be quite useful because you may terminate early on, right?
So do you mean to track at the type level,
Or,
the kind of timing bound on the branches that you are actually?
I think I misspoke in terms of types, but it doesn't really have to be types. If you do inference on conditionals, that's usually when we do taint-based propagation, timing side channel detection, we propagate on conditionals. And so my question was, can you extend this conditional, idea into the more formal, more programming language sense?
I guess it could be done. I don't see why it shouldn't be.
I see.
Possible.
Okay.
But always these are very like analysis. So
Yes.
if you want this for a general, this is gonna always be an over approximation.
Yes.
So, but I don't see why you couldn't.
Indeed, taints are over approximation as well, so that would be good enough.
Yeah. Okay.
All right. Thank you very much.
Okay, I maybe can do last quick question. So the calculus that you have right now, it's very limited. You don't have many features. So you have the monad, you have the up, but nothing else is really. It doesn't have any other effects. So I was thinking, would it be possible to extend this monad, for instance, with the references? Would this approach be able to show non-interference with this extension?
I will presume that there are some extensions that are doable, but we haven't thought about like more realistic in the sense of references or other stuff that are being studied in IFC. Like our first step was more to think like this language is strongly normalizing, can we do something in the other direction of general recursion before trying to tackle like references, concurrency.
Yeah, so I guess that one problem that you might have is that if you introduce references, then you lose strong normalization, and then you probably end up with the same. So yeah,
but it might be worth looking at.
Okay, let's thank the speaker again.